So in the last lecture we learned that we could write down a periodic function in terms of an infinite series involving sine nx, cosine nx, and the constant function 1. That is, I could write it as a sum of sine x, sine 2x, sine 3x, and cosine x, cosine 2x, cosine 3x, and so on. We also saw that the coefficients multiplying each of those functions basically told us how much of each of those to add in. So the coefficient a1 told me how much cosine x to add in. The coefficient a2 told me how much of cosine 2x to add in, and so on. Now the formulae for all of those coefficients, those integral formulae, I just stated them in the last lecture. And we're going to prove them in this lecture, so you're going to see where they come from. We're also going to see along the way a couple of neat little tricks we can use to speed up the calculation of these Fourier series. So here are those integral formulae for a0, an, and bn. They're the coefficients appearing in our Fourier series for my periodic function f. Now remember that we're focusing in this lecture on functions with a period of t is equal to 2 pi. So these formulae that are written down here are really relevant or appropriate only for the case of a periodic function with a period of 2 pi. It's very easy to extend these formulae for the case of an arbitrary period, and we'll see that in the next lecture. So again, for this lecture we're going to just focus on the case of a period of equals to 2 pi. So let's start off with a0. As we're going to see, a0 has the interpretation of just being the average value of my function f of x. So we want to prove that this formula is the one that's appropriate. And we're going to start off by expressing our Fourier series here. So again, f of x is equal to a0 plus cosines and sines. What I'm going to do here is I'm just going to integrate both sides of this equation from minus pi to pi. So integrating minus pi to pi of the left-hand side is equal to integral of minus pi to pi of the right-hand side. So let's tackle each of these terms in turn. So I've got a0 dx plus the integral from minus pi to pi of the sum n equals 1 to infinity an cosine nx dx plus the integral minus pi to pi of the sum n equals 1 to infinity of bn sine nx dx. So notice there that I really just split this summation here from n equals 1 to infinity into its two different pieces. So the sum over these ones and then the sum over these ones. Now those coefficients a0, an, and bn appearing here are all constants, so they can come outside of the integration sign. And what's more, the integration and the summation can be swapped around, right? I can always swap a sum with an integral. And the reason I can do that is because integration is a linear operation, so it doesn't care about sums. So we're going to pull out a0. We'll have the integral from minus pi to pi of dx plus sum from n equals 1 to infinity of an integral from minus pi to pi of cosine nx dx plus the sum from n equals 1 to infinity of bn, integral over sine nx. Alright, so let's tackle each of these in turn. I'll label them as 1, 2, and 3. So the first integral here is going to be 1. Let's just focus on the integral rather than the factor of a0. And the second integral will be integral 2, and the third integral will be integral 3. So let's start off with 1. This is a pretty easy one. Integral number 1 is integral from minus pi to pi of dx, which is just x evaluated from minus pi to pi. So that's going to give me pi minus minus pi. It's equal to 2 pi. So that's integral 1, relatively straightforward. Integral 2 is equal to the integral from minus pi to pi of cosine nx dx. So you notice that this is an even function. Cosine is an even function. And as we saw, cosine is, when I integrate over an even function from minus pi to pi, I can write that as 2 times the integral from 0 to pi. It's a useful little trick, and we'll use it many times. So the integral of cosine nx is going to be sine nx over n from 0 to pi. And so that's going to give me 2 over n sine of n pi minus sine of 0. But we know that sine of 0 is 0, and we know that sine of n pi is 0. Sine of pi is 0, sine of 2 pi, sine of 3 pi, sine of 4 pi, all of those are equal to 0. So I'm going to get 0 for my integral number 2. Let's take a look at integral number 3. So I've got the integral from minus pi to pi of sine of nx dx. And we notice that sine is an odd function. That is, when I swap it left-right, I get a minus sign. So the two contributions from 0 to pi and minus pi to 0 are going to cancel out, so that this total integral is going to be equals to 0. So we saw that integrals 2 and 3 both are equals to 0, so that means that I have, going back to my original integral, minus pi to pi of f of x dx is going to be a0 times integral number 1 plus 0 for integral number 2 plus 0 for integral number 3. We saw that a0, the integral 1 was 2 pi. So we have the integral of f of x dx from minus pi to pi is equal to 2 pi a0, which I can easily rearrange to give me an expression for a0. That's exactly my formula for the coefficient a0. Now we notice that this has actually got the interpretation that a0 is the average value of my function f of x. Because what I'm doing here is I'm integrating from minus pi to pi, so I'm integrating over an interval that's 2 pi long. I'm integrating my function, so I'm basically adding up my function at every single value of x, and then I'm dividing by the width of that interval. So I'm adding them all up, and I'm dividing by the number, so I get the average. So this is the average value of f of x. And this is a really useful idea, because in many cases, as soon as we sketch our function, it'll be very obvious whether or not what the value of a0 is, because it's going to be just the average value of that function. And so we can also interpret what A0 means. It's telling us how much do we have to shift up before we start adding in sines and cosines, right? When I'm trying to create the function f of x, I have to add in a certain base level, that's going to be A0, and then I start adding in sines and cosines, which oscillate about 0. So A0 is going to tell us the average value of f of x, which is sort of the base level that we're going to be adding into our sines and cosines. Notice that in this particular approach here, we were able to pick out or isolate A0 by integrating both sides of the equation and making use of the fact that the integral of sine and the integral of cosine from minus pi to pi was equal to 0 for any n equals to 1, 2, 3. So this is a very useful technique, and we're actually going to use this similar technique to isolate an and bn. But first of all, we're going to prove a couple of useful little integrals for trigs. So the first one is relatively straightforward. Example 2, I've got the integral of sine x times cosine mx, where m and n are both integers, so they're 1, 2, 3, and so on. Now this integral is fairly straightforward to show that it's equal to 0 because I can make use of symmetry. So sine nx is odd, and cosine is even. So I get the integral of an odd function, which of course is equal to 0. So the integral from minus pi to pi of an odd function is equal to 0. So that one's not too tough. Let's take a look at the next example. We've got the integral of cosine nx and cosine mx. So we're going to have to look at two different cases here. First of all, we're going to look at the case when m and n are integers but are not the same. And then we'll look at the case when n and m are integers and are equal to each other. So the case of m and n not equals to the same means that we can use the trig identity. Cosine times cosine is equal to the sum of the difference between the angles and the sum of the angles. So this is a trig identity you will have seen before. We're going to use this now to carry out the integral for the case of m not equals to n. So in that case, we're going to have the integral becomes integral from minus pi to pi of the sum of the two, so the difference of the two, plus a half times the integral from minus pi to pi of the sum of the two. Now, we've got cosine nx minus mx, so we can think of that as cosine times a frequency x, and we can think of this as cosine a frequency x, and so I can take the integrals of those things, and I don't have to worry about n minus m being equals to 0 because n and m are different from one another. So this thing is going to be equals to a half. Integral of cosine is going to give me sine x over n minus m plus a half sine n plus m times x all over n plus m. And we're taking those two integrals from minus pi to pi. So sticking all those values of x in, we're going to get 1/2 of sine n minus m pi minus a half sine, let's set x is equal to minus pi, so I'd get n minus m times minus pi, or m minus n, just reverse the sign. Plus a half sine of n plus m pi minus a half sine of minus n plus m pi. Okay, so I've just stuck in x is equal to pi and x is equal to minus pi into this and ended up with 4 different terms. But you notice every single one of these is sine integer pi. Sine integer pi. So n minus m, n and m are both integers, so their difference is an integer. Their sum is an integer. And I've got sine of minus an integer times pi. So again, every single one of these terms involves sine integer pi, and I know that that's always equal to 0. So all of these things will be equal to 0. So we see now that when n and m are different from one another, then the integral here is going to go equals to 0. So I've proved the first of these two cases. Now let's consider the case of m is equal to n. And we can again make use of another trig identity, but this time it's going to be cosine squared nx, that is cosine nx times cosine nx, is equal to a half 1 plus cosine 2nx. So again, integrating this thing, integral from minus pi to pi of 1 plus cosine 2nx dx. This is going to give me a half of x plus sine 2nx divided by 2n from minus pi to pi. Sticking in those values of x, we get a half of pi minus pi, pi plus sine of 2n pi divided by 2n minus pi minus sine of minus 2n pi. So we've just put in x is equal to pi and x is equal to minus pi in here. So the two terms that involve sine of an integer times pi, again, those are going to be equals to 0, but I've got these two new terms here. I've got a half pi and I've got a half minus minus pi. So those will add together and they will give me pi. So there I've proved that the integral of cosine nx times cosine nx, that is the integral of cosine nx times cosine mx when n and m are the same, it gives me pi. So we have this interesting situation here in this integral that this integral will be 0 unless n and m are the same integer. This is actually an idea that is related to the concept of vectors. We can say that two vectors form an orthonormal set or an orthogonal set if their dot product is 0 unless they're taking the dot product of the vector with itself. Right? So you can say a set of vectors is orthogonal to each other if each of those vectors has a dot product of 0 with every other vector, except of course when you take the dot product of the vector with itself. So you can see there's a very similar idea here with cosine. So we can see that we've got cosine integrated, which is kind of like a dot product for functions. We've got cosine integrated with every other cosine is going to be equals to 0, except when I'm integrating it with itself, in which case I get something that's not equals to 0. So we say that cosine is an orthogonal function. So now we're ready to prove the formula for an using this idea. What I'm going to do now is I'm going to isolate an by multiplying this function, both sides of this expression, by cosine mx and integrating from minus pi to pi. And then I'm going to make use of my formulae that I've just proved. So I've got multiply by cosine mx and integrate from minus pi to pi. And that's going to be equals to a0 integral from minus pi to pi of cosine mx dx, plus we saw that we could take the integration through the summation sign. We saw we could take it through the an. So I'm going to end up with the integral from minus pi to pi of cosine nx cosine mx dx. And likewise I've got plus the sum from n equals 1 to infinity of bn integral minus pi to pi sine nx cosine mx dx. So here again, all I did was I took my expression here, I multiplied each term by cosine mx, and I'm integrating from minus pi to pi. Now this is going to simplify kind of nicely because we recognize the first term here, integral of cosine between minus pi and pi. In the last example, we proved that that was equal to 0. So that's going to go away. Likewise, we've proved that the integral of sine times cosine is going to be equals to 0 because sine is odd and cosine is even. So that will go away. So that leaves me with this cosine nx and cosine mx. And we remember that we saw that this is going to be equals to 0 when n is not equals to m, and it will be equals to pi when n and m are the same number. So let's write out that in a little bit more detail. Remember, we're summing this up from n equals 1 to infinity. Cosine nx, cosine mx. So we can write that sum out in terms of every single one of its terms. So I've got a1 integral cosine 1x cosine mx. I've got a 2 integral cosine 2x cosine mx. A3, A4, A5, and so on. And let's say I keep on going until I get to AM. So I don't know what M is in advance. It's something that I specify. So I get to AM. I've got the integral from minus pi to pi of cosine mx times cosine mx dx. And there's all the terms greater than that. So am plus 1 all the way up to infinity. So I have all of my integrals now. And there's infinitely many of them. Cosine x, cosine mx, cosine 2x, cosine mx. All these all the way up to cosine mx, cosine mx, and higher orders. But only one of these integrals is going to survive because the integral of cosine nx cosine mx is equal to 0 unless they're equal to unless n and m are the same. So you can see that in all of these integrals here, they're all going to be equals to 0. So this one will be equals to 0, this one will be equals to 0, and so on. The only one that will survive is going to be this one. That is, when I finally get to m. So out of this infinite series, infinite summation here, I get a single term surviving, and that term is am times pi. So let's remember what I started off with. I had the integral from minus pi to pi of f of x cosine mx dx is equal to am times pi, and I can easily rearrange that to get the formula that I'm looking for. So that gives me am is equal to 1 over pi integral of f of x cosine mx dx from minus pi to pi. And the fact that I've got m's there instead of n's like we did in our formula doesn't matter much. I can easily just relabel these things so that they're n's instead of m's. There's no difference there at all. So we made use of the idea that the integral of cosine nx and cosine mx is going to be 0 except for the case when n and m are the same number. And so we use that to isolate am and to figure out the formula for am. Now the proof for the coefficient of bn is very similar. We're also going to make use of the fact that sine nx and sine mx are also orthogonal. By that I mean the integral of that will be equals to 0, and their integral will be equals to 0 when m and n are different, and it'll be equals to pi when m and n are the same. And we're going to use similar trig formulae to do that. So you're going to be able to prove that bn is equal to the integral of f of x sine nx all divided by pi. I just want to point out quickly here that you can kind of remember the formula for an and bn in a neat little way here. An is the coefficient multiplying cosine nx in my Fourier series, and you can see it's the product of f of x and cosine, so cosine and cosine. Likewise, bn is the coefficient for the sine nx in my Fourier series. And the formula for the coefficient bn is f of x times sine nx integrated from minus pi to pi. So then I'm going to leave that last bit as a proof for yourself to try. And I'm going to point out a couple of little useful facts that we can make use of in these calculations. The first is that my formula for a0, an, and bn were defined between an integral going from minus pi to pi, integral from minus pi to pi, integral from minus pi to pi. But remember that cosine and sine can always be picked up and moved over by 2 pi units to give me the same function. So what that means is that it doesn't particularly matter that I take my integrals from minus pi to pi in those integral formulae. All I have to do is make sure that I'm integrating over any given 2 pi unit. So as long as I have the lower limit of integration and the upper limit of integration being 2 pi apart, I'm free to choose them wherever I want, because after all my function is just repeating every 2 pi. So for example, you could also write these integral formulae going from 0 to 2 pi, 0 to 2 pi, 0 to 2 pi. They always have to give you the same answer. We're also going to make use of some of the simple properties of sines and cosines. And to do that, we're going to look at the following sequences. So let's write out the sequences for each of these, the first couple of terms for each of these sequences. So sine n pi, let's try n equals to 1, that would be sine of pi, which is 0. Sine 2 pi is 0, sine 3 pi is 0, and so on. So this is always going to be equals to 0 for every possible value of n. Cosine n pi is a little bit more interesting, right? So n is equal to 1, cosine of pi, that would give me minus 1. Cosine of 2 pi is 1, cosine of 3 pi is minus 1, so I'm going minus 1, 1, minus 1, 1. So we've already seen a nice little shorthand way of writing that, minus 1 to the power of n. So minus 1 to the 1 is minus 1, minus 1 to the 2 is plus 1, and so every odd number n times power of minus 1 gives me minus 1, and every even power would give me plus 1. Let's look at something a little bit more interesting here. Let's write out the terms for sine n pi over 2. For n equals to 1, that would be sine of pi over 2, so that's 1. Sine 2 pi over 2, so that's sine of pi, which is equal to 0. Sine 3 pi over 2, well, that's equal to minus 1. And sine of 4 pi over 2 is sine of 2 pi, which is equal to 0. So you can see that this is a sequence going 1, 0, minus 1, 0, 1, 0, minus 1, 0. It's basically going around the unit circle. So how do I write this down? Well, you see that every single even value of n here ends up giving me 0. So I can write this as 0 for n is equal to an even number, and I'm going to use the shorthand notation n is equal to 2k, right? So if I choose k is equal to 1, 2, 3, 4, 5, whatever I like, then 2k is always going to be even. What about n is equal to an odd number? Well, I'm going to write that as n is equal to 2k plus 1. So that's always going to be an odd number. I could choose k is equal to 0, for example. That would give me 2 times 0 plus 1 is 1. K is equal to 1. That would give me 2 plus 1 is equal to 3. So I get 1, 3, 5, 7, and so on. So I get all of the odd numbers using this little formula. So what is the correct expression now for my formula sine n pi over 2? What's the sequence going to be for the odd values of n? So you can see it's going n, it gives me 1, it gives me minus 1, 1, minus 1, 1, minus 1. So I can actually represent that as minus 1 to the power of k. Let's just check that. When k is equal to 0, I get minus 1 to the 0. Anything to the power of 0 is plus 1. And that corresponds to the value of n is equal to 2 times 0 plus 1, n is equal to 1, which was our starting value here. When k is equal to 1, I get minus 1 to the power of 1, I get minus 1. And that corresponds to a value of n equals to 2 times 1 plus 1, which is 3, which was this value here. So that was minus 1. So this formula here will work for even and odd values of n. Let's try a similar trick for cosine n pi over 2. So again, I'm going to write down the values of this for n equals to 1, 2, 3, 4. So n is equal to 1 gives me cosine of pi over 2, which is 0. Cosine of pi is minus 1. Cosine of 3 pi over 2 is 0. And cosine of 2 pi is 1. So I'm going minus 1, 1, minus 0, minus 1, 0, 1, 0, minus 1, 0, 1. So again, I'm going around the circle. And again, I can split this up into even and odd. So you can see that the odd values will be equals to 0. So n equals to 2k plus 1, that equals to odd numbers. And for n equals to even numbers, it's going to go minus 1, 1, minus 1, 1. So we're going to write that as minus 1 to the power of k when n is equal to 2k. So when n is an even number. So again, let's just check that. When k is equal to 1, I have n is equal to 2, so that corresponds to minus 1 to the 1, which is minus 1. When k is equal to 2, I'd have minus 1 squared, which is 1, and that corresponds to n is equal to 2 times 2 is 4, and that's 1. So these are useful ways of describing sequences in terms of their even and odd coefficients or terms in the sequence. So we're going to close up here with showing you how you can use symmetry to simplify the calculation of Fourier series. So let's start off with an example 7. We have a function that's x between minus pi and pi, and it's repeating itself every 2 pi. So this is a periodic function with a period of 2 pi. Let's start off with a sketch of this thing. Between, let's say, minus 4 pi and 4 pi. So pi, 2 pi, 3 pi, 4 pi, minus pi, minus 2 pi, minus 3 pi, minus 4 pi. And this is a function that is defined between minus pi and pi to just be the increasing function x. So it'll do something like this. Oop. Where we're going to include this value, but we're not including this value. And then this is the basic unit that we'll just repeat again and again. Okay, and then let's do the same over this side. Not all that easy to draw this on a device, but we're doing our best. All right. So there's our function, and it's repeating, and you can see that this clearly has odd symmetry. If I flip this left-right, I get minus of my function. I need to first of all flip left-right and then flip it upside down. So this function is an odd function. So let's think about what the coefficients of this function would be in its Fourier series, so the Fourier series coefficients. So A0 is the 1 over 2 pi integral from minus pi to pi of f of x dx. Now, I know that f of x is an odd function, and the integral of an odd function between minus pi and pi is 0. So a0 is going to be equals to 0. The average value of this function is 0. We can kind of see that from its sketch. It's just oscillating back and forth between minus pi and pi, and its average value is going to be 0. Now that's true for any odd function. Its average value is always going to be equals to 0 for an odd function. So the a0s are always going to be 0 for odd f of x. Let's try the ans. So we've got an is equal to 1 over pi integral from minus pi to pi of f of x cosine nx dx. So once more, I'm going to use the fact that f of x is odd. Cosine is even, so even times odd is odd. So I've got the integral of an odd function, which again is equal to 0. So without having to do any specific integration for a0 and an, I've found that both of those coefficients are equals to 0. So just stating that f of x is equal to an odd function is enough to tell me that a0 and an will vanish, and I'm left with bn. Now that's not going to go away because bn, remember, is the coefficient multiplying sine, and sine itself is an odd function. So when I'm creating the Fourier series for an odd function, I obviously want to include the basic periodic odd function sine nx. But we are in luck because f of x is odd. Sine of x or nx is odd. So we're integrating over an even function, which allows me to replace this with 2 times the integral from 0 to pi. Let's put in our formula for f of x. It was equal to x. And we're going to use integration by parts to evaluate this. So writing this as u dv, I'm going to get this is equal to u times 2 over pi, u times v from 0 to pi minus 2 over pi integral from 0 to pi of v times u. So that's minus cosine nx n times du, which is just dx. So let's pull out that minus 1 over n. So I'll get minus 2 over n pi x cosine nx from 0 to pi. Let's pull out the minus n, so that's going to give me plus 2 over n squared pi. Integral of cosine is going to be sine nx divided by n from 0 to pi. Sticking in those values of x, we're going to get, let's see, minus 2 over n pi, pi cosine n pi, minus 0, x is equal to 0, plus, let's pull out the factor of n. I think I had an extra factor floating in there, so there we go. So let's pull out that factor of n to give ourselves 2 over n squared pi times sine of n pi minus sine of 0. So we can see that those signs there, sine of n pi and sine of 0, those will be equals to 0. We also know that cosine n pi is equal to minus 1 to the power of n. So my coefficients here are going to be bn is equal to minus 2 over n pi minus 1 to the power of n. Or if you like, we could write this as 2 times minus 1 to the power of n plus 1 all over n pi. So we see here that we ended up with a function that had a Fourier series with a0 and an equals to 0, and it had non-zero values of bn. So that's going to be a really useful thing to remember whenever we're dealing with the Fourier series of an odd function. It's going to have only signs in it. So let's see what the Fourier series looks like for this function. So f of x is equal to the sum from n equals 1 to infinity of bn times sine nx. So we call this the Fourier sine series because it only involves sines. And you can see that that's only going to be the case when f is odd. Now you can imagine what would happen for the case of f is an even function. In that case, sine is an odd function, so I can't have any of sine in my function. Instead, I'm only going to get a0 and an not equals to 0, and all the bn's will be 0, which means that my function will have a Fourier series that only involves the constant 1 and cosine. So we would call that the cosine series, the Fourier cosine series. So just to sum that up, for any odd function, the Fourier series will be made up only of sines. We call that the Fourier sine series. And for any even function, we'll have a Fourier sine series that's made up entirely of a0s and cosines. So we call that the cosine series, Fourier cosine series. Now I've put up here a couple of links here for you to have a look at some interesting applets that you can use to play around with Fourier series. You're welcome to take a look at those and get a feeling for how cosine series and sine series actually work.